All right, in this lesson we're going to talk about how to calculate sy.x, which again is the standard error of prediction. It is an indicator of how good our prediction equation is and how good any one individual prediction is. And I do again have very good news for you. Presented the 5 columns that we've been using throughout this module at the top of the page. And again, the good news is that if you have calculated these 5 things, you've got everything that you need to have to calculate sy.x. All right. So again, just as a review, there's our x column. Sum of x is 25, x bar is 5. There's our y values. Sum of y is 45, y bar is 9. X squared is 165, or excuse me, the sum of x squared. Sum of y squared is 445, and the sum of xy is equal to 253. Now right here in the middle of the screen is the formula for calculating sy.x. Okay, so I probably should have set that apart a little bit better, but there it is. And so sy.x is equal to s sub y, and remember s sub y is the standard deviation in y, and times the square root of 1 minus r squared. All right, so sy.x is equal to the standard deviation in y divided by the square root of 1 minus r squared. So at various points on the paper, I do again, probably more as a review than anything, but I do the calculations for you. So let's start down here at the bottom, and I'll just draw a big square around this. Here's how you calculate the standard deviation in y. Again, there is our computational formula. And notice that we are talking about the y variable. So it's not the standard deviation in x, it's the standard deviation in our y variable. All right. Part of this you've actually already done. You can go back and look through your notes if you want to. But this number right here, that 40, is the sums and squares of y. Okay. So notice it is that number right there. Sum of y squared minus the sum of y quantity squared divided by n. And again, when I went down to this step, I did not show it, but that actually is 40. You can go back to our computational formula and find that. As a review, though, I went ahead and started from scratch and calculating the standard deviation in y. So again, standard deviation in y is the square root of the sum of y squared minus the sum of y quantity squared divided by n. All of that divided by n minus 1. Then I just plug and chug my numbers from my 5 columns, actually from 2 columns up at the top, and calculate the standard deviation in y to be 3.16. So I plug that into my formula, and then again, as a review, over here, I calculated r for you. Kind of draw a circle around that so that you can find it. And again, I'm not going to talk you through that calculation again. You've done that already. But r is equal to 0.7. So we square that. That's 0.49. And so now we're ready to plug and chug our numbers into our formula. So sy.x is equal to the standard deviation in y times the square root of 1 minus r squared. So for this set of data, that is equal to 3.16 times the square root of 1 minus 0.49, which is equal to the square root, or excuse me, which is equal to 3.16 times the square root of 0.51, which is equal to 3.16 times 0.71. So for this set of data, the standard error in prediction is 2.26. Now on the next page of this, we're going to talk about interpreting that, but before we leave here, I want to make a few comments, and you might want to jot a few notes down, because I think I want to spend a few minutes talking about what is it that actually affects our standard error in prediction. And so we're going to break down both sides of that formula. And so the first one is the standard deviation in y. So stop and think about it. Intuitively, hopefully, it should make sense that when we're talking about how good is our prediction of y, that is a function of the standard deviation in the y variable of the observed scores that we use to make the prediction equation. So if those observed scores are very variable, which is not probably a very good way to say it for you, but when the standard deviation in that y variable, those observed variables, is large, you're going to have not as good as prediction. So standard error prediction is going to be much larger. The standard error prediction is also a function of what is the relationship between x and y. The higher the correlation, the higher the r squared, and the lower the number under the radical. And therefore, the lower the number once the square root of what's under the radical is taken. So stop and think about it. I'll say it kind of again, maybe a little bit differently, but standard error prediction is a function of how variable is the y variable, the observed y variables that were used to make the prediction equation, and what is the correlation between x and y. Obviously, or maybe not obviously, but I'm going to tell you, we want our prediction to be as good as possible. And for our prediction to be as good as possible, we want our sy.x to be small, because that indicates we're doing a good job of predicting y. And so what we hope is that the standard deviation in y is low, and that there is a very high correlation between x and y. When that is the case, we will be able to do a better job of predicting y from x. Now let's move over and or move down the page and talk about interpreting this sy.x. So when we created our prediction equation, we found that our y-intercept was 5.5, our slope was 0.7, and we just previously calculated that our sy.x is 2.26. So on that, when we were calculating beta naught, beta 1, I gave you two x's to plug into the prediction equation, so we're visiting those guys again. And so our prediction for x equal 5 is that y prime will equal 9. So there is our interpretation of sy.x for y prime equals 9. 68 times out of 100, the person's true score on y would not be more than 2.26 units from 9, from that predicted score. For x equal 9, predicted y is 11.8. So the interpretation is that 68 times out of 100, the true score on y would not be more than 2.26 units from 11.8. So again, remember we're saying 68 times out of 100 because we are interpreting a sy.x as a standard deviation. And if we go one standard deviation above, one standard deviation below, which would means one standard error above or one standard error below the mean, we would be accounting for 68% of the people.